You're falling with the elevator. Elevator's falling, you're falling inside the elevator. How do you get to the floor? Check your neighbor on this one. How do you get to the floor? Because they told you, right? Oh, if you're going to be an elevator crash, you should spread yourself on the floor so that the area is bigger so the pressure is less, even though the force is going to be the same. How do you get to the floor? Check your neighbor now. See if your neighbor knows. How do you get to the floor? How do you get to the floor?
What?
All right, how do you get to the floor?
It just doesn't happen.
I mean, how am I going to get closer to the floor here? What do? I just bend my knees and I go down toward the floor, right? Here's the problem. If the elevator is falling out from underneath you, how do you get closer to it?
Go faster.
I mean, the thing is, you can't get closer to the floor. It's falling out from underneath you. If you were standing on a bathroom scale here, what would the scale read? The scale would read 0. Why? A bathroom scale tells you how much it's pushing up on you. But if it's falling out from underneath you, can it push up on you at all? No. So what would you be doing in the elevator cab as it's falling? You'd just be floating around. You can't actually get closer to the ceiling or closer to the floor. If you bent your knees, they would actually just come up toward you because the center of your mass has to stay in the same place. Because now there's no external forces. So if you bent your knees up, your knees would come up and your center would actually shift down a little bit. That's pretty funny to me. Right? If you tried to reach this way, your rest of your body would shift this way. You can't move. Right? Hopefully you're standing close to a side where you can like push yourself, right? Yeah.
So when you hear like on the internet and stuff and they tell you jump before it hits the bottom, that doesn't work.
Yeah, because you can't even get closer to the ground in order to jump. Right? But let's say that you started off knees bent, now the cable breaks, you're ready to jump, right? Keep in mind, the acceleration due to gravity is 10. The g value at the surface is 10, and that's meters per second, right? That means if it falls for 1 second, it's going to be moving 10 meters per second. That's 22.5 miles per hour. The g value is 22.5 miles per hour per second. If you fell for 1 second, you'd be going 22.5 miles per hour. Okay? In order for you to equalize the speed, you'd have to jump upward at 22.5 miles per hour.
Easy.
How fast do you think you can jump? 4. That's how fast you can jump. 4 miles per hour. Okay? That's it. There's also another problem with the fact that it's moving out from underneath you, so there's nothing to stabilize it. So if you push down on it, it's actually going to push up on you less because you just move it down farther. Think about it this way. This wall here says that if you fell for 1 second, you fall 5 meters. 5 meters is 16 and a half feet. Which means if you could actually jump that, you would go up 16 feet. How high can you jump? Like 10 inches. Maybe you guys can jump higher than that. Okay? So, no, jumping does not help. Because even if it only fell for 16 feet, still hits the ground going at 22.5 miles per hour. Even if you jumped at your 4 miles per hour, you still hit the ground going at 18 miles per hour. You want to get hit by a car going 18 miles per hour? No. Yes?
So how do you survive if you think of this?
Oh, you don't. I mean, you can, I suppose. Like, if you were to lay down and spread out all the force, so the pressure on any individual portion was less. But, I mean, you're going to break stuff if you fall. Right? And it's not you hitting the ground that's the problem. It's the ground hitting you. All right. So, back to this. If you are free falling and the thing you were in is also free falling, you are floating relative to it. Correct? That's what's happening over here. So, in the International Space Station, the whole thing, right, it is accelerating down toward the center, all the time, and all the people are in it also. It just also happens to be going, oh my God. It also just happens to be going forward at the same time. But remember, our bodies aren't speedometers. We don't feel speed. Our bodies are accelerometers. We only feel acceleration. Yes?
So if the only unbalanced force is towards the center of the Earth, how is its velocity perpendicular to that?
So you had to get it going at that speed. So the other day I drew like I drew the Earth, and then we put a cannon on top, right?
Oh, yeah.
Or we put a cannon on a mountain. So the velocity is this way, but because it's being pulled inward, it falls around.
Okay, that makes sense.
Yeah, so that's how to get in orbit. You got to get above the atmosphere for one, then turn 90 degrees and go perpendicular to the radius. And that's how to get in orbit. And that's what they do. Now, it's useful on Earth because if we draw the Earth, one thing we know about the Earth is it's already spinning on its axis, true? It's already spinning on its axis. So if I want to get my thing into orbit, I'm going to use the fact that the Earth is already spinning relative to the body. So that's why we launched from Florida, because it's far south. And the farther south you are, the faster the Earth is spinning. Right? You guys have a sense of that? Boy, this is super random. Up here at 42, where Detroit is, we do the same circle. We do our circle in 24 hours. Down here near the equator, they do a bigger circle every day in 24 hours, which means they actually are moving faster. Up here, we are moving at about 700 miles per hour. Down here, they're moving at about 1,000 miles per hour. So we launched our rockets that we want to get in orbit far south in Florida because it gives them that much more speed to get going. Isn't that so cool? You guys are like, Don, it is not that cool. I think it's very cool. All right, so here's the deal. Astronauts are continually in free fall in the thing that they're in, which is also in free fall. That's why they look like, or that's why it's not that they look like they're floating, that's why they're floating around. But the gravitational speed, or the gravitational acceleration, it's only a little bit less. Yeah?
They have to put it at a certain speed in order for it to orbit in the correct way.
They do. 100%. The speed is determined by the radius. So, if I think about it, the force concept here, right? I know that I need it to go in a circle, so the centripetal force has to be equal to the gravitational force. Right? So now if we're talking about the satellite, I'm going to go mv squared over r for centripetal force is equal to big G, big M, little m, all over r squared. These m's cancel. One of these r's cancel. And so speed where this r is the orbital radius. And again, in this case, it's the radius of the Earth plus the orbital radius, or plus the altitude. So the farther out you are, the actual slower you're going. Does that make sense? So yeah, so the if you want to go in a circle, you know how high you want to be, that determines your speed. Is that cool? Yeah?
So they launch things into space, they're mainly concerned about like the Earth's gravitational field.
Yes.
What's like the largest, like the sun would be like the largest thing they account for like other planets, you go farther out?
So other planets are very small and very far away. In terms of near us, it's the only thing that really matters is the Earth. So the gravitational force, because you have r squared in the bottom, the gravitational force in terms of the distance here, this is an inverse square law, and this thing drops off fast. I mean, twice as far away is a quarter of the force. If you're 100 times as far away, you're 10,000 times less. If you're 1,000 times as far away, then you're 1,000,000 times less force. The fact that it's inverse squared really dictates the fact that that it's the distance that matters. So even though the sun, so the Earth, the mass of the Earth is 5.98 times 10 to the 24. The mass of the sun is 1.898 times 10 to the 30th. When I look at that, so this is going to be, this is 10 to the 4th times bigger, okay? Well, 10 to the 4th is about 10,000, right? But we're talking about 200 miles, right? Versus 93 million miles to get to the sun. Does that make sense? So the fact that it's much more massive, but the distance is huge. It's huge. And then the other things are just super, super, super far away. So they only take into account when we're talking about like low Earth orbit for sure, they only take into account really the Earth. Maybe some small amounts of other things, but it's really just mainly the Earth. Cool? All right. Can we talk about my favorite thing now? So we have to pretend for a second that the Earth doesn't have an atmosphere, because the atmosphere just jacks everything up. So I want to throw a ball. So that when I throw it, it never comes back down. I want to throw a ball so hard that it never comes back down. How cool would that be? Right? I mean, like, now we're pretending for a moment that a couple things are true, that Earth isn't rotating and it's a perfect sphere, right? We're pretending these things, but like for real, like what? Because I know if I throw a ball, it's going to go up and come back down. Even if there's no atmosphere, it's still going to go up and come back down, true? The harder I throw it, the farther it's going to go, but still, it's going to come back down. How fast does it need to be moving when it leaves my hand so that it never comes back down? So this is something called the escape velocity. The direction doesn't matter, so you can call it the escape speed, but it just is what it is. And here is how this works. I want this ball, as soon as it leaves my hand, it's going to start slowing down, true? So it's going to slow down, 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 slow down. Yes? When's it eventually going to come to a stop? Way out there, right? So it's going to come to a stop. The speed is going to be equal to 0 when we're going to use r for distance here. It doesn't mean radius here, it just means like a distance vector, is equal to infinity. I want my ball to slow down forever. Because this way, it's never going to come back. Does that make sense? Like, you got to kind of think about it a little bit. Makes my head hurt. Kelly's like, how many more minutes left? How many more minutes? Now, here's the thing. At any moment along here, this ball's moving here. Would you say it has some energy? What kind?
Kinetic.
Is it moving? Yeah, it has some kinetic energy, right? How do we find kinetic energy? Good. Where m is the mass of the ball and v is the speed, yeah? Does it also have some gravitational potential energy? It does. Do we have a way to calculate the gravitational potential energy? Do we know? How do you calculate the gravitational potential energy?
MGH.
All right, so this is like our moment. Again, we're going to have some cognitive conflict. When we're on the surface of the Earth and it's flat, okay? When we're near the surface of the Earth and it's flat, and I have my ball, and it's here, at a height h, we know that the gravitational potential energy is equal to mgh. Is that cool? Now, how did I get it there? I had to lift it up, true? So I had to really do work on it, right? So work, as a general idea, is the force times the distance. Right? You guys with me on that? So what this means is that my work, well, what is the force on the ball? It's just mg, and what was the distance? H. So I'm saying that here, the amount of work I had to do to get the ball there is equal to the amount of energy I store in the gravitational field. Is that cool? But this is only near the surface of the Earth. What is the force on this ball by the Earth? Isn't it G, M Earth, M ball, all divided by R squared? That's the force, right? So using our same understanding that the work is the force times the distance, okay? If the work is the force times the distance, what do you think this is going to be equal to? G, M Earth, M ball, all divided by R squared, but then times what? Times R. Because we did the force times the distance. You see that what that says there? They are in this case. So the R is whatever distance it's at, and we always measure from the center, right? So in this case, R is the force distance. It's the distance at the forces. And so what we're left with then is that the gravitational potential energy near a planet or a sun or some sort of gravitational body is going to be equal to G, this time mass of the Earth, times mass of the ball, just divided by R. All right. Now, this next part is really, really important. Very hard to understand, but super important. So what's going to happen here then? I want to find out what my total energy is. Okay? Well, how are we going to calculate total energy? Total energy, E total, is equal to U plus K. So if you're ever looking for total mechanical energy, it's the U plus the K. That's a general idea. Fair? What is happening over here? If I want my ball to reach speed v when the radius is infinity, when the distance is infinity, what is the energy situation over here? Check your neighbor, see if your neighbor knows. What would the energy situation be over here when my ball reaches zero speed at infinity? What's the energy situation? Check your neighbor now, see if your neighbor knows.
Gravitational, like intensity increase in gravitational.
What's in the R's at the bottom?
Oh, you're talking about that. So then, wouldn't both be on the zero then? Kinetic energy?
All right, what do you think? What's our total energy situation over here? Yeah.
All gravitation.
maybe, except for what's my problem? If I look at my gravitational energy formula here, it's equal to G m1, that's the mass of the Earth in this case, mass of the ball, all divided by r. Where's the r? It's in the bottom. What happens to your total thing if you take your r and you let it go to infinity? What does it do?
Go to 0.
It goes to 0, right? So, when I get out here at infinity, my total mechanical energy is equal to U plus K, but 0 plus 0. Think about that. So, way out there at infinity, my total kinetic energy is 0, my total gravitational energy is 0, or approaching 0, because you can't ever get to infinity. You think you got to infinity, but infinity is infinitely far, so you just got to keep going. I think my favorite thing, and one of my favorite things for math, is if you take infinity plus 1, it's still equal to infinity. It's like my favorite. Yeah?
So with that potential gravitational equation, wouldn't it, the further away you get, the smaller it gets?
Yes.
But usually with the other one, the further away you get, the bigger.
I know. Wait till you see what we do to accommodate that. It's the dumbest thing, okay? So Nick makes a good point. He's like, I feel like we're upside down on this one. That's because we are. So what we're going to do now is we're going to take our ball, and we're going to start out here at infinity, and we're going to let it fall back. So it starts out, it's at infinity, the velocity is 0, but it feels the gravitational force from our planet. So what's it going to do is it starts going this way. It's going to speed up, right? Here's the problem. There's no external forces here. We're just talking about the forces between the ball and the Earth, right? This gravitational potential energy is the gravitational potential energy of the Earth ball system, because it has both things in here, right? There's no forces outside the Earth ball system. So in a technical sense, as the ball moved this way, the Earth would move this way, but it's so much bigger, we're just going to say it's only the ball moving. Is that cool? So what happens to the speed as it goes this way? As it moves this way, you have a sense that it's speeding up, so what's happening to the K value? It has to be going up. But there's no external forces, so what does the total mechanical energy have to equal? Still has to be 0, which means that the U value has to go down. But it doesn't make sense that it would go down because R is getting smaller, so the whole thing should get bigger. So here's what it is. You ready? Don't miss it. To accommodate this, they actually changed the definition from this, which makes conceptual sense, to this, which makes more mathematical sense. So our actual definition for gravitational potential energy is negative G_mm over R. So this accommodates Nick's problem. It says as you're getting farther away, yeah, it's approaching 0, but it's actually getting